Yeah, hi everyone. So thank you everyone for introducing yourselves. This is the deep learning course, and some of you guys said that you want to learn about machine learning. So first off, let me tell you that I'm teaching two courses this semester. One of them is statistical machine learning. The other one is deep learning, which is this. And I think these two together become the union of these two becomes machine learning. Okay, the whole machine learning. I'm saying you can see statistical machine learning as machine learning minus deep learning, and deep learning as just neural network based machine learning. Okay, so if you want to learn the basic algorithms in machine learning, which are based on statistics and not neural networks, the other course does that. Also, feel free to take both courses if you would like. And yeah, that's one thing. So what else I wanted to say? Okay, yeah, I will. You'll see that. Oh, by the way, yeah, this course you said that about the theory, the prerequisites. So I think first off, between these two courses, statistical machine learning and deep learning, the statistical machine learning has a bit more theory. That's one thing, but that's more basic. And but both courses have theory. So I can say in summary, I think the only prerequisite for these two courses is being patient with math. Okay, especially in the other course. So you shouldn't get frustrated by theory and mathematics. That's one thing. You should try to enjoy it, bear with it, and you will enjoy it. And also, what else? So, yeah. Also, a little bit knowledge of calculus and linear algebra might be useful, although I try to build from nothing. So we'll build from nothing, and we put bricks one by one, and we come up. Okay, that's it.
Forgot to mention one thing. Last semester, I took the course statistical machine learning under him, and this is the second reason I'm taking deep learning is because of him. He's one of the best professor.
Oh, thank you very much. I appreciate it. Thank you for your kind word. Okay, yeah. So yeah, as I said, we try to build from nothing and we come up gradually, but having some knowledge of calculus and linear algebra might be useful, because as you will see, machine learning is nothing but optimization plus some other things such as linear algebra, probability, and statistics. So nothing but these. Okay. The other things might be illusions. Okay. So this is machine learning. And yes, let's see what we are going to cover in this course. So this course focuses on various topics in deep learning, covering topics from fundamental concepts in neural networks to state-of-the-art deep learning. Okay. So we'll start with one neuron only one neuron. So we have several algorithms for only one neuron: perceptron, Adaline, logistic regression. These are only for one neuron. And then we make it only one layer neural network. And we have at least two things for one layer. One of them is radial basis function network, or RBF network, and the other one is self-organizing map, or SOM. And then we go and make it several layers, and it becomes feed-forward neural network. And for that, so we will introduce activation function and the parts of the feed-forward neural network, and then we will cover backpropagation, which is nothing but gradient descent plus chain rule. So you know chain rule in derivatives, right? Derivative of A with respect to B, you can see it as derivative of A with respect to C times derivative of C with respect to A. So, and it is just gradient. Gradient descent is gradient descent. What is gradient descent? It's just first order optimization. Okay. So by the way, some of the initial sessions of these two courses might be a bit repetitive so I apologize if you have if you have both courses, some topics might be in initial sessions will be a bit repetitive to you. So when you have an optimization, unconstrained optimization problem, you minimize or maximize some function, right? So assume I say minimize f of x, like this, with respect to x. It's an unconstant, there is no constraint for it, okay? How can we solve it? They things, if it is wrong, that's fine. How can we solve it? We cite in high school or college, so it's not very complicated. Exactly. We take derivative and we set it to 0. We set it to, so we exactly as we did in high school. We wanted to find the minimum or maximum of a function. We take derivative, we set it to 0. So let's take derivative and set it to 0. If we do that, it will either, we should try to find x equals something, right? So we find the minimum or maximum or something. Assume I find it. Assume I can find it. And if I can make x in one side and the other things in the other side, it gives me a closed form solution for x, right? Now, this x, this added page. So what did I do? Minimize f of x with respect to x, derivative of x with respect to x, set it to 0. Assume I can find a closed form solution. We know that when I have a function, where do we have the derivative equals 0? It's either maximum or minimum or saddle point. This is saddle point. This is maximum. This is minimum. The minimum and the maximum are also called extremums, right? So how can I find out whether it's minimum or maximum or saddle point?
Second order.
Second order derivative. Exactly. We learned this in high school or college, depending on where you have been raised. Okay, so here, if derivative, what does the sign of derivative show me? The second derivative, I mean. So the sign of first derivative means whether the slope is upwards or downwards, right? The sign of second derivatives tells me whether the face of the function, the face of the ball of the function is upwards or downwards. So here the face is downwards, so its second derivative is negative. Here the face is upwards, so its second derivative is positive. And here sometimes it is upwards, sometimes it is downwards. So we can easily calculate the second derivative and see its sign in a neighborhood around that point. This is in one-dimensional function. If it is a multi-dimensional function, if it is like a surface, then the second derivative becomes a matrix. It's called Hessian matrix. We will cover it. We'll see that. And the Hessian, now the matrix, it doesn't make sense to say whether the matrix is positive or negative. In that case, we should say whether the Hessian matrix or the second derivative is positive semi-definite or negative semi-definite. We'll talk about it, but what is, in simple words, what is positive semi-definite and negative semi-definite? Positive semi-definite means that is all of its eigenvalues, the eigenvalues of the matrix, are non-negative, either positive or 0. And all of negative semi-definite means that all of its eigenvalues are non-positive, either negative or 0. By the way, please feel free to interrupt me and ask me whenever you want. Don't need to raise hand and see me as your friend, okay? Don't see me as a professor or something. Let it be a discussion based and think, and also interrupt me whenever you want. And also, you said that you have there is a gap between in your education. That's fine. If there is any part that you don't understand, ask me. Okay, feel free to interrupt me and ask me. So, did you find out about what I said about the eigenvalues and everything? The positive semi-definite. What? Yeah. Okay, that's good. So this is now a question. What if I can't find a closed form solution? Assume this derivative is very complicated, such as tangent of x with square root of sine of x over x, something like that. I can't find a closed form solution for x. Assume the derivative is this. I can't find a closed form solution. What should I do?
Approximation.
What? Approximation? Yeah, but how? So what is this? Assume this is a function. Consider the derivative of that function is another function, right? So that function equals 0. What does it mean? I want to find its roots. Right? I want to find its roots. How can I find the roots of a function if I can't find a closed form solution? Have you passed any course in numerical analysis? Exactly, the numerical analysis course tries to answer this question: how to find the roots of a function iteratively, numerically. We should do that. Okay. One famous algorithm for that is Newton-Raphson algorithm. Newton-Raphson algorithm. So we should start with some random solution and we iteratively update it until we converge to some root, right? Exactly, we do the same approach for solving derivative of f of x with respect to x set into 0. So we do it numerically, and depending on whether and this is called numerical optimization. And depending on whether we use the first order optimization or first order derivative or second order derivative, it's called first order methods or second order methods. If we use only first order derivative, also called gradient, that's called gradient methods. The most famous one is gradient descent. If we use both first order and second order derivatives, this is called second order optimization, and that's usually called Newton's method. Newton's method. So that's for unconstrained Any questions so far? Did you get it?
What is the algorithm you mentioned before?
Which one? So I said gradient descent.
For that, the
Newton-Raphson. Newton-Raphson.
one you need to approximate the.
Find the roots, right?
Yeah.
To find the roots is Newton-Raphson, for example. Newton-Raphson is simple. So I say Newton-Raphson, you have seen this game, I think, a lot. At least we had, I remember we had a TV program in Iran. Everybody played it wrongly. So the best way to solve this game is Newton-Raphson. So I say I have a number in my mind in range 0 and 500. Guess it. And you need to do it with the least number of guesses. How do you do that? That's exactly Newton-Raphson algorithm. You say you in the middle. That's also called because they're related. So that's also called binary search. So you can say, let me have this range, 250. You guessed 250. I said whether it's above that or below that. Then if I say it's below that, so you get rid of the upper half and say now between 0 and 250. The middle thing is 125 or something like that. And then you do it until you converge to the solution. This is the fastest way. So that's why to converge to the solution. That's why Newton-Raphson's method is the fastest way to find the roots of the function. And Newton's method, unconstrained Newton's method, can be derived from Newton-Raphson. So if you apply Newton-Raphson on this, it gives you Newton's method. For more information, I have a course, Optimization Techniques, in my YouTube channel. Feel free to see that for more information and details on these algorithms in optimization. Anyways, why did I say these things? Because as I said, in machine learning, we are always optimizing something. We are minimizing or maximizing something. You are either minimizing some cost function or maximizing some fitness function. And then in deep learning, also, we are always minimizing a cost function or a loss function. Therefore, we need to optimize it. And in deep learning, we usually use first order derivative only. Why? Because we are lazy. We're lazy, we don't want to calculate second order derivative. it's hard. It's hard sometimes to calculate the second order derivative. So we say, let's only find the first order derivative or gradient. And that's why backpropagation for training neural networks is just gradient descent. However, the variables in the neural network we will see later in this course that depend on each other. Why? Because we will see that we have several layers. The cost is at the last layer here. So the value of this depends on this. The values of weights depend on the weights in the next layers. Therefore, when we have dependence in derivatives, we have to do chain rule. Okay? And by the way, if these are vague for you, I'm just having a fast review. We'll go into details. Okay. So we have to have chain rule, and therefore it's gradient descent plus chain rule, and that's backpropagation. That's exactly what Hinton et al. Proposed years ago, I think in 1980s, and they named it backpropagation. Okay, so just very fast, I tell you that what happens if it is constraint optimization, minimize f of x subject to some constraints, for example, x less than 5 or whatever.
Convex optimization.
Yeah, convex optimization, but what is how can we solve? So if it is, there are several algorithms for solving convex optimization, but in simple words, what is the most famous algorithm for solving convex optimization? That's called interior point method. Okay, interior point method. It's out of the scope of this course, just for your information. Interior point algorithm, also called barrier methods. The name seems scary, but the algorithm is very easy. That's just generalization of Newton's method for constraint optimization. Right? Newton's method is just for unconstrained optimization, right? But what if I have constraints? Then they simply generalize that. Very simple. If you go to the theory, see my YouTube channel, YouTube video for interior point method. You'll see it's very easy. In 10 minutes, I think you will find out how it works. And they call it interior point algorithm. And it's the most famous. Many of the optimization toolboxes are using interior point algorithm. Another technique is that you convert this constraint optimization problem to an unconstrained optimization problem. There are several ways to do that. I think, why am I emphasizing on this? Because when you understand optimization, you understand a lot of things. Let me tell you a bit more about that, and then we'll continue with the course. So here, minimize f of x with respect to x subject to some constraint. Assume g of x less than or equal to some 0. Assume. So let me convert it to an unconstrained optimization. How? There are several ways. I can say, let's penalize it. So g of x less than or equal to 0, it means that I want g of x to be small, right? Therefore, I can have it added to the actual cost function, and I know that I'm minimizing the cost, right? Therefore, I'm also minimizing g of x here. This is called regularized cost. F of x is cost. This is called regularized cost, and this lambda is called regularization parameter.
The difference with this one with Lagrange.
Yes, Lagrangian, you can interpret it as a regularized cost. So you can see, if you don't know what Lagrange is, that's fine. If you know, you can see Lagrange function as a regularized cost function. Okay, so you are doing this, and then it is an approximation to this. Approximately. Why? Because for solving this, you have to satisfy gx less than 0. But for this, you are penalizing it. Doesn't necessarily become less than 0, right? You're approximating. What if I want it to be exactly the same and become unconstrained? There's another way. Another hack you can say. Yeah. What is this? Indicator function. It's one if its condition is satisfied. Sorry, in here, it's zero. In optimization, it's a bit different. In indicator function in optimization is zero if its condition is satisfied. Otherwise, it comes infinite. What do I mean by this? It becomes zero if x is less than zero. Else, it becomes infinite. Then what happens? I'm minimizing this. For this to be minimized, this needs to be zero because it's either zero or infinite. If it is infinite, it kills the optimization, right? It blows the cost, right? This is indicator, right? This indicator, as you see, is like this, right? Right? Theoretically, it's very nice. Can we implement it in computer? No. Can you implement infinite in computer? No. So let's approximate this again. Let's approximate it by some logarithm function. We can approximate it by logarithm function. That's why they call it log barrier. The interior point algorithm actually is this. See? The interior point algorithm uses that technique. As I said, these two are exactly equal, right? However, these and these are approximately equivalent. Okay, I think it's enough for an overview of what optimization is. Okay, any other question?
The one with lambda parameter is the approximation with the optimization problem.
The lambda says how much should I weight satisfying the constraint compared to the actual cost.
I mean, why that is the approximation to the original optimization problem?
Which one?
The first one,
Okay.
regularization one,
Yes.
why you say that is a
Approximation.
yeah.
Because in the actual cost, which is in the actual optimization problem, you have to satisfy gx less than 0. Here, gx might be 0.0001. From 0. Small, but not less than 0. Right? Okay. So we will cover backpropagation, which is gradient descent and chain rule. And then we'll cover stochastic gradient descent. So for backpropagation, there are two very famous optimization algorithms. One of them is a stochastic gradient descent, and the other one is Adam. If you have worked with PyTorch or TensorFlow, usually these two options are the most famous ones. We'll cover both. Also, in the meantime, we'll cover AdaGrad and RMS prop, which are required for understanding Adam. Also, we will cover convolutional neural networks and important CNN architectures. Several of them, I think, we will cover, for example, AlexNet, DenseNet, UNet, GoogleNet, Inception. These are the famous CNN networks which were proposed by famous companies such as Google, Facebook, and this. Then we'll cover regularization techniques such as weight decay, batch normalization, dropout. Then we'll cover sequence modeling. One of you guys said time series. So sequence modeling or time series modeling, it's useful for NLP, natural language processing, for text processing, and also speech recognition or speech processing. And we will cover in this category recurrent neural networks or RNN, LSTM, long short-term memory networks, attention mechanism, transformers, BERT and GPT. Okay. I think you have heard of ChatGPT a lot. So yeah, we'll cover how it works. And by the way, attention mechanism is a backbone for BERT and GPT and these things. So ChatGPT also its backbone is transformers, whose backbone is attention. And attention is nothing but, let me tell you an example. So when you look at Mona Lisa portrait, do you see everything with the same eye? Do you notice every pixel in the image equivalently? No. You notice her face, her lips, but you don't care whether there is a river behind her. Right? Initial glance, right? So you attend to some parts more than the other parts, right? Also, when you are doing fast reading a text, do you read do you attend or do you focus on the words equivalently when you are doing fast reading? No. Do you care about all of the word? You get rid of the the's, these things, am, is, are, and this. So you will care about important words. You attend to some words more than the other ones, right? Therefore, we can use the same thing which we have in our visual system or in our mind mathematically. And how can we model this attention mathematically? How can we do that? What? You were saying, so using simple similarity. So when I say something attends to the other thing, it means that they are related to each other. They're more similar to each other, for example, right? Or they are more opposite to each other. They are kind of similar to each other. And when you're so similar or related to each other mathematically, you can implement it using simple inner product. Inner product of vectors means how much similar they are to each other, right? And attention mechanism is nothing but that. Okay, we'll see that. We'll see. ChatGPT, the whole foundation of ChatGPT is inner product of words to each other. This word attends to the other word more than that word. Okay, we'll cover deep metric learning and Simon's network. So in simple words, deep metric learning, what does it do? It's a part of dimensionality reduction, and that says that if I have some data points which are similar to each other, let me push them toward each other. So they become more closer to each other. If they are different from each other, let me pull them away. This is metric learning, deep metric learning. We do it using deep neural network, hence the name deep metric learning. And one of them is Simon's networks. We'll also cover generative models. We'll cover variational models. We'll cover variational inference and variational autoencoder. We'll also cover GAN, generative adversarial network, and adversarial learning. I think this term, last semester, I didn't have time to cover generative moment matching network and diffusion model, but I think I try my best to cover them in this semester. So what are the generative models? What are they doing? They do some kind of magic. What do? They get some noise, they output a real data point. Okay. Assume I get some noise. I output some facial image, which is realistic. This is what generative models do. They are generative, they generate data. And depending on the time, the other covered topics can be Boltzmann machines, restricted Boltzmann machines. One of the initial neural networks was Boltzmann machines. Graph neural networks, which are neural networks for graph data. Knowledge distillation for network compression. So we can compress the networks. Why do we need to compress networks? Can you tell me?
Complexity.
To transfer them, to make it easy to relay the information from one point to another.
Make it easy to relate information
To
from
relay the information, because
relay information from
like one point to another.
one data center to another data center, something like. What do you mean by one point to another?
I read this in a research paper that they compress the data that is extracted from a hyperspectral image, because it's a very dense data set. So they compress it to transfer it over the internet.
But that's data, right?
Yes.
Here I'm talking about compressing network itself, not data.
Reduce complexity.
Maybe reducing complexity, maybe, but I think the most important reason for that is implementing networks in embedded systems in your phone. If you have a huge network, you will have memory error. You don't have enough space in your cell phone, for example, right? Many cell phone companies are actually using network compression. They can't have the whole GPT or BERT networks in their phones. They have to compress it somehow, right? And one of the techniques for doing that is knowledge distillation. What is that? The ideas are very simple and very interesting. So I have the big network and I call it the teacher network. I have a small network, a smaller version of this network. I call it student network. Then I can distill knowledge from the teacher network to the student network. How? The student tries to mimic or imitate the behavior of the teacher, right? In this way. So, and how can I do that? Loss function can be how this is similar, how the output of this is similar to the output of the teacher, right? So as I said, everything is minimization or maximization of something, right? Minimization of difference of these two outputs. This is knowledge distillation. Now, what if my network, my teacher network is too big and my manager in the company says, we don't have a space. It needs to be too small. So the difference of teacher and student is too much. What should we do? What do we do in real world in education? We have teacher, we have a student, we also have TAs, teacher assistants. So we can have teacher assistants in between. Teacher assistants learn from teacher, and also students learn from teacher assistants, something like that. Okay. So we can have deep if time, but usually that time doesn't allow us to go to deep reinforcement learning. But we have them in mind if time allows. Meta learning just simply means learning how to learn. Okay? And they are usually used for few shot learning. So what do I mean by few shot learning? When your training data points, the number of training data points is small. You don't have too much data to train. How can I generalize well using a small training data? Federated learning. What is federated learning? Federated learning is just distributed deep learning. It's called federated learning. Why do I need distributed?
Privacy.
Privacy is one of the reasons. Why? Because when I have several servers, these servers don't see each other, right? For security or privacy is important. Another reason, I don't want to have the whole overload in one server. So I can divide tasks, right? Explainable AI. What is that? This is explainable AI. It says that, how can I explain whether my machine learning algorithm is working well or not? If it is working well, how can I explain it? Whether it's working by chance, or has it learned actually? One technique for finding out the explainable AI is what? Saliency map. And what is that? It says that assume assume I'm learning some, for example, I have some classification algorithm and some images, right? Then assume some dogs and cats and these things. And now, after training, I feed some image of dog to it. It tells me it is dog. However, I can have a saliency map. I can come back from the last layer to the first layer gradually and see which part of the image has a network focused more. How can I do that? Simply, I can say, let me take derivative of the output of the network with respect to the input of the network, the pixels of the network. And it tells me which pixels are more important for the output. This gives me a map. And if I do that on a trained neural network, what happens? It tells me that the pixels around the dog are more important than the pixels of the background. That's called saliency. And self-supervised learning, what is that? It simply means that let me generate my labels myself. Let the network generate the labels itself. And also theory of optimization in neural networks based on pack learning, etc. If time allows, we don't know how much of these we can cover. And some applications of deep learning, including usage in computer vision, image processing, and NLP. Okay. This is a tentative schedule of weeks, but it's tentative. I usually don't care how much we can cover in each lecture. The course materials, lecture notes will be provided to you in course link. We have a YouTube channel for the course, and we will upload the videos of the lectures to the YouTube, so you can watch them later also. But it doesn't mean that you shouldn't come to the class. The class is in person, and please come to the class and participate in it. I strongly believe that you will learn much better if you participate. And also, I have some tutorial papers. You can take a look at them. And in some of the materials that I'm gonna teach are based on my tutorials. And some of them also have become the chapters of a book named Elements of Dimensionality Reduction and Manifold Learning. So additional resource for the interested students, Professor Ali Quds's lectures at the University of Waterloo and available on YouTube. I think that's very good. His lectures are very great. Also, the Carnegie Mellon University Deep Learning. I think they also have very good lectures on their YouTube channel. So additional books, these are optional, and it's not mandatory to read them, but if you want to learn more, you can take a look at them. Also, I have ordered them in the University of Guelph, so they are available in the bookstore of the university. Some of them, their PDFs are also available, I believe. So these Elements of Dimensionality Reduction and Manifold Learning is our own book, my book. And you can, it's in the bookstore also, I think, if you go by the VPN of university, you can download this PDF, I believe. The other book is Deep Learning of MIT Press by Ian Goodfellow, Benjo, et al. And the PDF of this is also available. So the PDFs are available. There is a very good book named Understanding Deep Learning. It's gonna be published soon by Prince in MIT Press. And I think that's also a very good book. And we also have Pattern Recognition and Machine Learning by Bishop. And research articles in the literature. And of course, this website, by the way, introducing me, I'm Benjamin Gojo, and this is my email address. It's better that if you have any questions, you ask your questions in the Microsoft Teams group that I will make, and you join, please. The course does not have any TA, unfortunately, this semester, because according to the rules of university or department, the courses with less than 30 students don't have any TA. So last semester it had a TA, but this semester it doesn't have. And we are, I think, 25 Yeah. Only 5 more we have TA. So classes will be in person. Discussion chats and questions will be in Microsoft Teams group. I will make one and I will ask you to join. Also, whenever you ask any question, please mention or tag my name because Teams doesn't notify well usually unless you tag me or mention me. You can also mention the whole group if you want to talk to others also. The course's web page, this is a public website of the course. I haven't put yet anything in it, but I will put gradually the stuff in it. However, I seldomly update these. I update the course link more often. So I think if you track course link, that would be easier for you. Yeah, always check for the notifications of the course link. Okay, I will make announcements. I will put stuff in there. Also, I will put videos to YouTube channel. I will eliminate the personal information of the students. Course evaluation. So as we don't have any TAs, we will not have assignments for grading, but I will give you assignments just for you to practice. So assignments, we will probably have 2 assignments. I will put assignments in course link and I will give you due date. You will solve them by yourself for the sake of learning and joy. There is no upload for it. So you do it, and after the due date, I will post the solutions so you can check your answers. And I strongly suggest that you do the assignments because you learn better. Also, the midterm exam usually is similar to the midterm exam, to the assignments. The midterm exam is now 50%, so I have increased it. It's grading because of not having assignments. It will be somewhere in which sometime between the semester. But I will announce the date, exact date in the future. And it will be open book because I don't want you to memorize anything. I'm strongly against memorization. So you try to understand everything. And it doesn't mean that being open book doesn't mean that you should study in the exam, right? Because you won't have enough time. So study beforehand, understand everything, and the exam will be open book. The course project will be 40%, and sometime in the middle of the semester, I will ask you to form teams. I will let you know how many students per team, and then you will write proposals, 1-2 paragraphs only. The proposals will not be graded, just for the sake of verification. And I will verify them, and if that's fine, I will say go ahead. And you will have enough time until the end of the semester. In the last day of the semester, the last day of the classes, I mean, for the last class that we have, you will come and present your projects. And group presentation is 10%, so everybody in the group needs to present. And also, as I said, so it's during class time. The midterm is also during class time. So basically we have 12 sessions. One of them is midterm, the other one is presentation. The 10 others I will lecture, okay? And what else? Yeah, I think, the report and the code will be 40% the course project. Also, after the during the presentation, I and other students will give you feedback, and you will have 10 days to apply the feedback on the projects and finalize it and submit the final reports and codes. Bonus points for participation in the class, participation in discussions, asking questions, answering questions, interrupting me, and participate in discussions. That's very important. I don't want to be the sole speaker, okay? Again, don't see me as a professor, see me as a friend. We are gonna learning all together, okay? And don't worry about your marks. If you do your best and do all of the tasks, give good grades. And you can ask the previous students of the courses that I have had, they will ensure you that I give good grades. If required, I will curve the grades. So you need to worry about that. In my courses, you shouldn't think about grades. You should only think about learning and joy. Okay? Enjoying the course. I have said it multiple times in my courses. When you are participating in my courses and learning, it should be like that. You are watching the YouTube channel of Stanford or MIT. Do you care about your grades when you are watching courses on YouTube? No, you don't care. So exactly here, you shouldn't care. You only do your best. It doesn't mean that you should become lazy. Do all of the tasks and do your best, and I will give and make sure that I will give good grades. So focus on understanding. Don't worry about your marks. I'm a good grader. Also, we'll try the course to be good for both industrial projects and academic research. And it will have theory, and I will make sure that it also is useful for practice. And ask questions. I don't want to be the sole speaker. Any question? No. So usually this is how I teach. So we will usually stay until the end of the classes, but we'll have breaks in between. So we'll have 15-minute breaks, but we stay until the end. Why? Because we need to cover things, and yes, otherwise we can't cover things. I strongly believe that the professors, for you also who want to be a teacher or professor, we should stay until the end. If we finish sooner, it means that we are not doing our job correctly. So that's one thing. Okay, so let's have a break and come back at 8:25. We'll continue. That's good. Is that good? 8:25. Okay. Thank you. Hey everyone, let's continue. So, by the way, I was just notified that the number of students in the class has become exactly 30. So I need to ask the department whether it's too late to have a TA or not. If they add a TA, then I will adjust the grading. I was thinking that we just became 30 students. Maybe the department will add a TA. I'm not sure. Let's see. I need to ask them. It might be too late for them. Accordingly, I will adjust the grading if we have a TA. So let's go with preliminaries, data set, learning model, and learning tasks. Okay, consider a measurement, the measurement of a quantity. Okay, so consider the measurement of a quantity. This quantity can be anything, right? Such as personal health data, including blood pressure, blood sugar, blood fat. It can be images from a specific scene, but taken from different perspectives, right? For example, you have the images from a sculpture with different angles. Or images from several categories of animals, such as cat, dog, frog, etc. You can have medical images, for example, digital pathology image patches, also called histopathology image, or including both healthy and tumorous tissues. You can have CT scans, etc., or MRI. You can have any other measured signal. Okay, then this quantity can be multidimensional. So it can be either univariate or one-dimensional. It means that it is a scalar, right? Or it can be multivariate or multidimensional. What do I mean? It has multiple dimensions, multiple features, right? For example, consider a vector of health data, which has the first feature is blood pressure, the second feature is blood sugar, and blood fat, etc. Okay, so it can be multidimensional. That is a set of values. Therefore, every quantity can be considered as a multidimensional data point in a Euclidean space. What is Euclidean space? The simple spaces that we usually work with in high school, that's called Euclidean space. Okay, so this quantity that I'm talking about can be a vector, a multidimensional vector. And we know that every multidimensional vector in the Euclidean space can be seen as a data point. So data point is equivalent to vector. Why? Consider this space. This is a point. It can be seen as a vector connecting origin to that point. Right? Okay. Let the dimensionality of this space be D. D standing for dimensionality, meaning that every quantity is a d-dimensional vector or data point in Rd. Why do I call it Rd? R to the power of d. It means that d-dimensional Euclidean space, because usually we are working with real data rather than complex data. The set of d values for the quantity can be called the features of that quantity. Features or dimensions. Okay. Multiple measurements of a quantity can exist. So far we talked about the quantity itself. Now I'm saying that multiple measurements can happen. For example, I have some blood pressure, blood sugar, blood fat. You have some blood pressure, blood sugar, blood fat. You also have another one. So each of us has some vector. Right? Therefore, now I have several vectors or several data points. Now let's put them together. If I put them together, I will have data sets, a set of data points. Right? And a set of d-dimensional data points or d-dimensional vectors. For example, the quantity can be an image. If the quantity is an image, what does it mean? Its features or dimensions are its pixels. Why? Because you can reshape an image to become a vector. The data set then can be the images, different images from that scene with different angles, for example, or different images of different animals. Now, learning model. Now we have introduced data set. Now let's go to learning model. Consider a data set of n data points, x1 to xn. What do I mean by this? It means that I is x1 until xn, right? I goes from 1 to n, each of which is the dimension, right? In the d-dimensional Euclidean space. Now I have n vector, each of them is a vector, right? This is a vector. This is a vector. I can put these vectors next to each other column-wise. This becomes a matrix with d rows and n columns, right? Usually in this course, I denote scalars with small case, vectors with bold small case, matrices with bold capital case, sets with fancy capital case, such as this. Right? This is set. Okay. So this is my usually notation. And we have n points, so n columns, each of which is d-dimensional. This X is data set, right? Matrix of data set. Now consider a learning model F, which is a map from data space to some output space. So it maps from d-dimensional Euclidean space, also called input space, to a p-dimensional output space. So it maps X to f of X. Map is something in mathematics. Functions are maps, but not all maps are functions, right? Usually P is less than or equal to D, usually, but not always. This is a learning model F, which takes X and outputs f of X, and as the dimensionality of f of X is usually less than X, the length of this I have put smaller than the length of the input. Let me open the door, it's a bit hot. So now this learning, the whole purpose of machine learning is to find the parameters of this f. So it gets x and outputs what I want. Learn this f to output what I want. This is machine learning. For this, you can consider this machine learning model f as a newborn baby. It knows nothing, the newborn baby. Now consider this example. So again, I apologize if you have heard these in the previous course. So consider a newborn baby. Now I'll assume I have some cucumbers and some tomatoes.
I'm just curious, what would be an example where you're mapping to a higher
Dimension?
Yeah.
It is possible.
like an example? You have one.
Usually, we have sub-modules which map to higher dimensions, and that they are called kernels. For example, we have this in kernel SVM. I covered that in the other course, the statistical machine learning. So when we have non-linear classes, I can't separate them with linear support vector machine. Support vector machine or SVM is a linear classifier. It can't separate two non-linear classes, non-linear separable classes. I can map them to higher dimensions, and then using the linear classifier, I can separate them. For example, consider. So the question was, what if P is in what example P is greater than D? Saying that this is an example. So these are non-linearly separable in 2D. I can increase the dimensionality in 3D. So they become something like this. So I bring one of them up. And then using a linear classifier, I can separate in a linear plane. Okay. So this is called kernel technique. We have at least two techniques for kernelization in machine learning. One of them is kernel trick. The other one is using representation theory. I cover both of them in a statistical machine learning course. So yeah, that was an example for where P is greater than D. But usually P is less than D. Okay, so does it answer your question? Okay, now let's go back to our example. I have a newborn baby. I want to teach the baby the differences of cucumber and tomato. What do? I say in one example, I bring several tomatoes and cucumbers. I tell the baby, I show a cucumber and say, this is a cucumber, this is another cucumber, this is another cucumber, this is a tomato, this is another tomato, this is another tomato. I show 100 tomatoes, 100 cucumbers to the baby. Then the baby learns that this is tomato, this is cucumber. And then I show a new cucumber to the baby and I say, what is it? It will answer me probably it is cucumber. I will show a tomato, which it will say it's a tomato. That's called classification, because I'm showing the classes of tomatoes and cucumbers. Now in this example that I have taught the baby cucumbers and tomatoes, after this teaching, what if I show the baby a carrot and I ask, what is it? What will the baby answer? What? Tomato? Cucumber. It will say it's cucumber, because among cucumber and tomato, which one is more similar to the carrot? That's the cucumber, right? Why? Because the world or the mind of the baby is only understanding cucumbers and tomatoes, doesn't know any carrots. If I want, also another example, if I show an apple to the baby, it will say it's a tomato, because apple is more similar to the tomato. If I want the carrot and apple to be added to the world of the baby, I should also show several examples of the carrot and apple, and I say this is carrot, this is carrot, this is tomato, this is apple, this is apple. Then the world of the baby becomes 4 classes: carrot, apple, tomato, and cucumber, right? And here I'm telling the names of these groups or categories or classes to the baby. So this is carrot, this is cucumber. These names are called labels in machine learning. Labels. This is called classification. Now consider another example that this time I don't just tell the baby this is tomato, this is tomato, this is cucumber, this is cucumber. I put all of the tomatoes and cucumbers in front of the baby. I said, baby, I will respect your understanding. I don't tell you this is tomato, this is cucumber. I respect your understanding. Based on your own understanding, try to separate these into two groups. Okay. The baby will look at them, will say, okay, these are round and also almost red. So I put them next to each other. There's the tomatoes. Also, these are lengthy and green. So I put them next to each other and it separates them into two groups. This is called clustering in machine learning. Okay. If I ask the baby, what is the name of this group? I assume I point to the tomatoes and I ask the baby, what is the name of this group? What will it answer? What will the baby answer? What? It will say nothing because there is no name for it. You can name it anything. You can name it Benjamin, right? You name that group Benjamin. This is Benjamin. This is desk, right? It doesn't care about the name. In other words, it doesn't care about the label. It only cares about the patterns of them, of each group, and separating these patterns. Right? This is called clustering. Clustering in machine learning. In the classification, we are using labels, so it's supervised. When we are using labels, it's supervised. When we are not using the labels, it's called unsupervised. So clustering is unsupervised, and classification is supervised. Now another example. I want to make an artificial leg for people who don't have any leg. So I go to a healthy leg and I measure the EMG signals near the joints. Okay. Now in the healthy leg, I will ask the person to have different angles of the joint, and then I record the EMG signal. So I will have a lookup table of different angles and different EMG signals, right? So, but I can't cover the whole range of angles. This is continuous. No matter how fine my steps are, I can't cover the whole thing. Okay. Now, using a technique named regression, also called prediction, I try to interpolate and extrapolate this table. Right? The whole purpose of regression or prediction is to interpolate a lookup table and extrapolate. Otherwise, any idiot can memorize a lookup table. Memorization of lookup table is not an art. Right? The art is interpolate. So here now, after I have this, I learn some regression model, and then I put the artificial leg on the person without a leg. Then that person gives me some EMG signal. The regression model will see that this EMG signal is kind of between the EMG signal of 40 degrees and 45 degrees. So its degree must be something 43. So it can interpolate. So this is regression. And again, some other examples, we can have regression for time series. For example, stock prediction, weather prediction, right? And these. Okay. And as you see in regression, we are using labels. We are using here in the example of artificial leg, the labels were the angles. The inputs were EMG signals, the labels were angles. In the weather prediction, the inputs are features of the, for example, pollution, coordinate, and these things. The output is the weather, the temperature, and these things, right? In the stock prediction, the input, the features are closing price and these things, the different prices of the day, and the output and the window of the previous days, and the output, the label, is predicted closing price in the tomorrow, for example.
What is the intuition for call it regression?
Regression is another name for prediction, because we are predicting.
Like you're analyzing, if like talking about angles, so you're taking like an unknown set. So like if you have a lookup table and you have a signal, you have a value from a signal which is not in the lookup tables, but you can still look it up into the table and you can guess. So that is how the regression model works.
Yeah, it doesn't look up in the table. So how does the regression model works? It has some parameters. It learns these parameters using this lookup table, and then using these parameters, it can predict whatever you give it. So, and again, based on how complicated your regression model is, it has different errors. For example, if it is too complicated, for the lookup table, its error becomes 0. So what do I mean? For example, for this EMG signal, for EMG signal A, it gives 45 in the lookup table. Then after training, your regression model also, if you give A to it, it will give you exactly 45. However, for the other unknown things, it will interpolate and extrapolate. However, if it's not too complicated, even for the lookup table, it will have some error. So when you give A, it will give you 44.5, for example. This is regression. Okay. And as you see, labels in regression are continuous. Continuous. Range, right? So here, some examples are f of x can be R, the output of the learning model can be real value, or can be in the range, or between 0 and 1. D-dimensional between 0 and 1. Okay. However, in classification, the labels are discrete and usually finite. So, as a result, you can see classification as kind of a special case of regression. Clustering, you can see that it groups into M groups, but the labels of the groups, you don't care. You only care about grouping. We have also reinforcement learning. It's similar to training a dog. When you want to train a dog, you will give when you want it to do something, some specific tasks, and not to do some other things. Whenever the dog does that good thing, you will give some sweets to it. Otherwise, you don't give sweets to it, right? And initially, the dog does something random. If it repeats the random things, and sometimes we give the sweets to the dog. Gradually, the dog, after doing some random tasks, it will find out there is some correlation between some of the tasks and eating the sweet. So it will repeat those good things more often, right? This is exactly what we do in reinforcement learning. So we have good positive rewards and negative rewards, and we see the machine learning model, the learning model F, as a dog. Okay? So the output of the learning model is action. What to do based on the environment. Okay, and this A is the set of action, the possible action. We can have dimensionality reduction, also called manifold learning. What does it do? It takes a d-dimensional vector and outputs a p-dimensional vector. And in this case, p must be less than or equal to d, because we are reducing dimensions. And usually p is much less than d. Okay. It's either supervised or unsupervised. In unsupervised dimensionality reduction, we are not using any labels. So basically, what do we do? Means that the main idea of unsupervised dimensionality reduction is that I have some high dimensional data points. Each of them has some pattern, right? Has some features. I want to map them to low dimensional space, also called embedded space. I want to map them to an embedded space so that the more similar points, the similar points fall close to each other, and dissimilar points fall away from each other. As you see, I'm not using any labels. I'm using the patterns of features. This was proposed mostly by locally linear embedding. Supervised dimensionality reduction is, it uses labels, and its main idea is usually is this. So I have classes now. I have classes. And I want, in this mapping to the embedded space, I want the points in the same class to fall closer to each other, and the points in different classes to fall away from each other. And that's called supervised dimensionality reduction. So in other words, I want to reduce the intra-class variances and increase the inter-class variances, variance between classes, right? This idea was first proposed by Fisher discriminant analysis, or FDA, also called LDA in the literature.
Any real world applications for these two tasks?
Oh, too much application. So what is the use of dimensionality reduction? A lot of uses, but the most famous use I can say is feature extraction as a pre-processing. So what do I mean? Consider a classification problem. You give some raw data to it. It classifies it for you, right? Now, suppose you do dimensionality reduction or also called feature extraction as a pre-processing. It separates the classes better, and then you feed it to the classifier. Of course, the classifier will perform better. Right? Consider this example. Example of this that I also mentioned previous minutes ago. These two are non-linearly separable. If I give it to a classifier which is linear, what happens? Accuracy might be awful. Maybe worse than random classification. Maybe 40%. 40% means it's worse than flipping a coin, right? So then let me add feature extraction as a pre-processing. What does the feature extraction do? So it gets this, and it, for example, outputs this. Then I feed it to the classifier. Of course, the linear classifier can simply classify them. Then the accuracy becomes 100, for example, or 90%. So you can use that as a pre-process. So for more information on dimensionality reduction, you can see our textbook available here. Elements of dimensionality reduction and manifold learning. So numerosity processing also is, so I'm giving you different examples of different learning tasks, right? Outlier or anomaly. So now, rather than working on dimensionality, I can work with the samples or instances, right? I can have outlier or anomaly detection for detecting outliers in data. Why do I need to detect outliers in data? Why do I need that? Can you tell me?
The noise.
Remove the noise, exactly, because when I have noisy data, if I feed it to the classifier or whatever, it might perform very poorly. One example, one use is this. Another use is fraud detection, exactly. So in the, for example, credit card fraud detection. So in the first use, noise is bad for me. I hate noise. In the second use, noise is good for me. I love noise. I want to detect noises, right? My money is in detecting noises. So prototype selection is selecting important instances. So you can see it kind of as the opposite of anomaly detection. You want to find good representatives of the data. Yes.
Just curious, could you name some algorithms for anomaly detection?
So some algorithms for anomaly detection, for example, isolation forest or local outlier factor, in short LOF, one class SVM. There are some others too, I forgot. Ellipsoid method, so it fits some ellipsoid or Gaussian distribution on data, whatever it is, its standard deviation is high, is outlier. Yes, I think the most famous ones were these isolation forests and a lot of variants of it. and LOF, one class SVM, ellipsoid method, and these things. Okay, so prototype selection selects important representatives of data, and prototype generation, in addition to selection, it generates some important data points, good points. Right? For more information on that, you can see my PhD thesis. Okay, there are some other fields of AI. For example, soft computing. Soft computing is another field of AI, and usually it has two main things: fuzzy logic and fuzzy control. So fuzzy logic is a protest against binary logic. So when I say, "Are you well?" you can say yes or no, right? That's binary logic. But you might say, "I don't want to say yes or no. I want to say I'm 70% well." So I'm neither well nor not well. I'm just 70% well. So it's a range, continuous range, fuzzy logic. Also meta-heuristic optimization and intelligent search. So that says, just briefly, I say that it's when the optimization problem is too hard or you have too many constraints, then maybe you can't use classical optimization that we discussed minutes ago easily. In these cases, you say, let me search. Let me forget math and just search. And you can do search in various ways. You can do it in the dumbest way, random search. Randomly, let me search some solutions, see which one is the minimum. Gives me the minimum cost, for example.
We call it soft, and is there any opposite direction of soft computing?
I think they call it soft computing because it has less math, I guess. As I said, materialistic optimization is an intelligent search.
So it's the opposite of for the problem where we have like closed form mathematical problem. Is that like the opposite?
Yes, so in at least in optimization, that's called the mathematical optimization is usually called classical optimization. Like first order optimization, second order optimization, and these things. Those are math heavy. People who love math, they usually love that. People who love math and they're in mathematics or optimization departments, they hate materialistic optimization. They say it's just playing games. It's not the true science or something like that. So like, the materialistic but however, materialistic optimization can be very useful practice in industry and these things. So materialistic optimization is search. So as I was saying, assume I search. The dumbest way is random search. Random search. However, it's dumb. It's not good. Another way is to do grid search or brute force search. Let me make a grid and I search with fine steps. I search all possible solutions, right? However, it's not good, right? Because of time complexity, it takes forever to search the whole space, especially for high dimensions. Then let's do a middle case scenario. That's intelligent search. And what do we do? So and a quick example, I need to go very quickly over these things because it might be repetitive for some people. So assume I want to find some treasure on the ground, under the ground of this room. Okay. Then assume we are 3 people who want to find the treasure under the ground of this room. As I said, we can randomly dig, or we can do grid search. However, it takes forever. Or we do it in a wise way, also called materialistic optimization. For example, I say you dig there, I dig here randomly. You dig there, okay? And then I say in this situation, I found plastic, you found gold, you found diamond. Among these, what is the best? Diamond is better than gold, gold is better than plastic. So we to move toward that global best so far, the diamond is better. Let's slightly move toward that. However, we don't go completely there. Why? Because what if there is a better treasure in the middle of the way? Okay, so I move slightly toward that person. you move slightly toward that person also moves, searches locally. And then we search in the next iteration, we search locally. Then we announce our findings. You say, you found now plastic. I say, I found two diamonds. You found some bronze or whatever. Now 2 diamonds is the best now. So the global best has been updated to 2 diamonds, which is my finding. So now the other 2 person move toward me. And we do it iteratively. We do this procedure iteratively. This is the particle swarm optimization algorithm, one of the meteoristic optimization algorithms. As you see, intelligently, wisely, we are finding the treasure, right? And these 2 are usually called soft computing. If you want to know more about this, I have a 3rd course, which is in this semester, and that's in University of Waterloo. And I'm covering soft computing in that. I'm also putting the videos of that course on my YouTube channel. You can watch them. So we also have biological inspired or 3rd generation neural networks. Some example is spiking neural network. So it's a relation of neuroscience and cognitive science. Also, we have feature engineering as a feature pre-processing. So feature extraction, I already explained, that's called dimensionality reduction. What is feature selection? So I have dimensions or features. I can either transform them or map them to another space where P is less than D, right? This is what I explained already. But feature selection says rather than this transformation, let me select from the features. I don't do the transformation. I just simply get rid of some of the features and remain the other ones, right? So when you select some features, that's called feature selection. When you transform the features to become less number of dimensions, that's called feature extraction. How can we do feature selection? The ideas are very simple. You need to think about it and you will see it's not very complicated. Assume I have some features, I have some label, and I want to find the best features. Give me some suggestions. How can I find?
Rank the score.
Score them. Let's score them and get rid of the worst scores. But how can we score the features?
The features that are giving us the best results, the closest results that we expect, they will be considered the best. And so we can like reduce features on the scale that the features that are giving us the best results, they are the selected ones, and we can reject the other ones because the model will still work if those are removed.
Okay, so I summarize and repeat because of recording. So you said let's find the features which give us the best result. For example, best classification accuracy and distance, right? Or best regression output. It means that, so that's correct. That's one of the methods to, one of the approaches to select the features. Those are called wrapper methods. So the feature selection algorithms are broadly divided into 2 categories: wrapper methods and filter methods. Wrapper methods is exactly what he said. It's, let's select the features so the accuracy or whatever we have at the output improves, right? Because we wrap them over the classification, or because this is pre-processing, right? Pre-processing of what? Something. Let's wrap it over that so we see the result of that. That's a wrapper method. Filter methods, however, is more statistical. What does it do? What?
Maybe filtering out more important features than the less important features.
Yeah, but how can we find more important features using statistics?
Through their labels.
Labels, exactly. So we should see the relation of labels and the features. So we can simply, for example, calculate the mutual information or correlation between the features and the labels, right? So if I have mutual information or more correlation or more relation of some feature with a label, it means that that feature is more important for that label. Let's keep it. What if I don't have label? What is it? What if it is unsupervised?
And we can find out the patterns.
The patterns, yeah, kind of. We can find the relation of the features, the relation of features to each other, rather than the relation of feature to the label, right? In this case, if two features are correlated or much more related to each other, I should get rid of one of them because they're repetitive. They have repetitive information. So this is feature selection.
What's the difference between the meta heuristic and the heuristic algorithm?
Oh, meta heuristic and heuristic, although it's out of the scope of this course, but let me tell you a bit. So heuristic algorithms, they are designed for a specific application. Meta heuristic says, I don't care which application, which cost function, which optimization you have. I design an algorithm which can be applied on different optimization cost functions.
General?
Yes, more general. And also application of AI in different fields of science and technology. So this was a brief introduction to AI. So I told you what AI is. Now let's get more into the preliminaries of the theory. By the way, preliminaries are usually the most important parts of my courses because I refer to them a lot. Okay. So linear projection. You might be wondering, why is it related to, how is it related to deep learning? It's all related. You can see every layer of neural network as a linear projection before activation function. Before activation function, every layer of neural network is just a linear projection. You will see that. Okay. First off, let me define some terminologies and this. I usually try to explain everything and build from nothing. So if you don't understand any part, let me know to explain again. Consider P basis vectors. What do I mean by basis vector? So every P-dimensional space has P basis vectors. For example, one-dimensional space, if it is origin, this is its basis vector. Right? What do I mean by basis vector? You can represent every point in that space by a linear combination of its basis vector. So you can, for example, say, what is this point? 3 times this, for example, spectrum, right? So in 2D, these two vectors are basis vectors. I can have in 3D also, I have 3 basis vectors, x, y, z, for example, right? So consider this point here in 3D, assume this is the origin. Then this point can be represented as this vector, then this vector, and then this vector. Right? Okay. So when I have p-dimensional space, I need p basis vectors. We define a p-dimensional Euclidean space by these p basis vectors. For example, 2 vectors define a plane, 3 vectors define a 3D space. Okay, now in terminology, nothing hard, just terminology. These p basis vectors, we call them, they span the p-dimensional Euclidean space. It's another name for saying that these are the basis vectors of this space. I can, in other words, I can say these basis vectors span this space. Nothing complicated, just naming. These basis vectors span this space. Or the other way around, this space is spanned by these vectors. This space is spanned by these basis vectors, spanned by the p basis vector. So far clear?
Meaning that the space can be represented as a function of the 3 vectors.
No, as a linear combination. So every point in this space can be represented as a linear combination of these basis vectors. What do I mean, by the way, by linear combination? I think you understand. So for example, I have u1, assume here I have u1, right? Linear combination is alpha u1, alpha 1 u1 here in this one dimension. When I have this point in 2D, I can say alpha 1 is some value, 1.3, for example, whatever. So, or it can be positive, negative, right? Alpha 1 u1 plus alpha 2 u2. Alpha 1 u1 plus alpha 2 u2, as you see, it's a it's linear, right? I don't have any nonlinear function here. Linear combination, I'm combining them, I'm summing them up. Right? Okay. Any other question? Everything is clear? Okay. consider the P vectors U1 to UP. Okay. Let's put them column wise next to each other. So U1 to UP, if I put them next to each other, assume each of them is D-dimensional. D as dog. P is as Peter. Okay. So I have P vectors, each of which is D-dimensional. If I put them next to each other column wise, it will give me a matrix U with D rows and P columns. Do you agree? Right? Again, another terminology. The space spanned by the columns of matrix U is called column space of U. So what do I mean? What is column space of U? Consider the columns of the matrix U. You can see them as the basis vectors of some space. Let's call that a space column space. The column space of U is the space spanned by the columns of matrix U. We denote it by this column of U, the span of U1 to UP, where U is D by P. In other words, the space whose bases are the columns of matrix U is called the column space of U. Okay. So we talked about column space. Now let's talk about linear projection. Assume there is a data point X D-dimensional, right? And we have P vectors U1 to UP. Each of them is D-dimensional, and P is much less than D. Usually it is much less than D. It can be equal to D2, but usually it is much less than D. So the matrix U, whose columns are U1 to UP, is D by P dimensional, right? D rows and P columns. What do I want to do? I want to project X onto the column space of U. And I will tell you what it means. I want to project X onto the, I already defined the column space of U, right? In the previous slide. Now I have a column space of U. I have a data point X. I want to project it into that. As P is less than D, usually P is less than D, as I said. Then at most P is equal to D. Usually P is less than D. Then if P is less than D, I will have subspace. This column space is called subspace. Why? Sub means below, right? Because it has less number of dimensions than D, right? Because P is less than D, so I call it subspace. So the projection of this X D-dimensional X onto this column space, which is P dimensional. The column space is P dimensional. You agree? It's defined as equation 3. U transpose X. Let's see what it means. What is X? What is dimensionality of X? It is D by 1. U is one column. It's column vector, right? What was U? U was D by P, right? Here. D by P. What is U transpose? P by D, right? So U transpose is P by D. Therefore, this matrix multiplication makes sense. P by D times D by 1. The whole thing becomes P by 1. Therefore, this is P dimension. I denote this matrix multiplication by X tilde. You can call it Ben, whatever. Naming is not important in mathematics. Okay? The math is important. Don't confuse yourself with naming. U transpose X, I call it X tilde. As you see, I transformed X from the D dimensions to become P dimension. Right? This is called linear projection. And column space was P dimensional. So I'm projecting it onto a P dimensional space. It's a column space of U. Okay. I can reconstruct this back to become D-dimensional again. So it was D-dimensional. I projected that to become P-dimensional. Then I reconstruct it back to become D-dimensional again. So I had x tilde. If I'm left multiplied by u, not u transpose this time, by u, this becomes d-dimensional. Let's see, I can replace x tilde with u transpose x as in equation 3. So I will have u transpose x, right? What was x? D by 1. What is u transpose? P by d. What is u? D by p. So the whole thing makes sense. D by p times p by d times d by 1, the whole thing becomes d by 1. So it's d-dimensional. I denote it by x hat. My notation, right? A good thing about mathematics is that you are the owner of variables and you can name them yourself. When you write a paper, you name the variables, they are like your children. You name them. Okay. So I named them x hat. And this became, so as you see, x was d-dimensional, it became p-dimensional, and then it became d-dimensional back. Right? It's called reconstruction. So far, we understood it mathematically. Let's understand it intuitively. What it means. Consider this two-dimensional space, x1, x2, right? Two-dimensional. And this point x in it, which is two-dimensional, this point. Right? Then consider the column space of U, let it be one-dimensional. So only this. This is column space. So here, P is 1, D is 2. Do you agree? D is 2, P is 1. I want to project this to two-dimensional X onto the column space of U, which is one-dimensional. Of course, by project, I think if you have seen projection anywhere in mathematics, it's orthogonal. So the projection will be orthogonal. Right? So the projection will be here. By the way, did you understand why the column space and the two-dimensional space, all of them pass through this origin? You know the reason? First off, we have one origin. So they have to pass from the same origin. And why do we have to have an origin? Because when we have a vector space, these spaces are called vector space because we can represent every point as a vector. Every vector space must have origin. Why? This is one of the properties of the space. Because in a space, we should have linear combination of the elements of that space. The linear combination of the elements of the space must be in that space. Okay, must. However, one of the simplest linear combinations is something minus itself. X minus x, which is 0, which must be in that space. Therefore, every space must have the origin. Right? Okay. So we understood this origin, and we know this. Now we project x onto this space. It became here, x hat. Now you tell me, I can see this point. If I'm pointing here, I can see it in 2D or 1D. Do you agree? I can see it in this line of column space or in this 2D. In two ways I can see it. If I see it in one-dimensional column space, that's projected data point. That's called x tilde. Right? So what do I mean by seeing it in the line? When I see that in the line, I don't care about how rotated this column space is in the 2D. So I can say this is column space, right? This was origin. Only this distance is important to me. This is U transpose. Only the distance from the origin, one-dimensional, is important, right? I don't care about the rotation. However, if I see it back in the 2D, it's reconstructed. As you see, reconstruction doesn't necessarily equal to the original point. Right? There's some difference between them. So you have some reconstruction error, also called reconstruction residue. Right? When is x equal to x hat? when is x equal to x hat? Is it possible that we have zero reconstruction error? Yes, when x exactly is on the line. If x is on the line, column space, then its reconstruction becomes itself. Do you agree? So it means that if my point is already in the column space, its projection falls on itself, right? As I said, we have some residue or error between x and x hat. So residue is x minus x hat, x minus u transpose x. If you know about machine learning a bit, have you heard of PCA, principal component analysis? That's one of the algorithms in machine learning, not in this course, in the other course, the statistical machine learning. It just minimizes this reconstruction error. As I said, machine learning is nothing but optimization plus some other things. See? PCA is optimizing this, minimizing this reconstruction error.
Why do we need linear projection in machine learning?
Okay, why do we need linear projection in machine learning? Because I think bravely say that all linear algorithms in machine learning have linear projection. Linear projection is the backbone for all linear algorithms in machine learning. Examples: PCA, FDA, some people call it LDA. All of these are having linear projection. Also, interestingly, some of the nonlinear algorithms, not all of them, some of them are linear projection plus some nonlinear function. Neural network is this. Neural network is a linear projection, nonlinear activation function. Linear projection, nonlinear activation function. You see that? It's very crucial and important in machine learning. Now, norm. Inner product, let's define that. First off, inner product, also called dot product. Consider two vectors d-dimensional, x1 to xd and y1 to yd. By the way, what is this? This is transpose. Okay, why do I have transpose? Because I want it to be column vector. Usually, in machine learning, we consider vectors as column vectors, usually. So this is also a column vector x, this is a column vector y. I denote it by these. I can say it also, I can denote it by x transpose y or y transpose x, doesn't matter. It's just saying that multiply the corresponding elements and sum them up. I think you might say, this is childish. Why are you telling us? This is easy. We learned it in high school or first year of undergrad. Okay, I say that's fine. But we have inner product of matrices. That's a bit more complicated. What is that? Consider two matrices, x and y, with d1 rows and d2 columns, the same size. Okay, I have their inner product as trace of x transpose y. So I have trace of x transpose. Here, I have trace. Why? Why do I need trace? Why do I need trace?
Inner product will be scalar.
Exactly. The result of inner product must be scalar. X transpose y here is matrix. I have to make it a scalar. And trace makes the trace output of trace is a scalar. What is a trace if you don't know trace? What trace is? Trace is nothing complicated. It's just, first off, the input of trace is always a square matrix. It can't be a rectangular matrix. And it is the summation of its eigenvalues. The summation of eigenvalues of the matrix is the trace of matrix. It is equivalent to the summation of diagonal elements. Okay. As you see, the output of trace is a scalar, and I have to have it as a scalar. Why didn't I have trace for the scalars? Actually, I dropped it. Why? Because trace of a scalar is equals to itself. Trace of A equals A if A is a scalar. Okay. And its definition is similar to that. Multiply the corresponding elements, sum them up. Okay. This is norm. Now, this was inner product. Now norm. Norm, a function norm, takes RD and outputs R, d-dimensional vector. It can also get matrix, doesn't matter. Its output is scalar. It's norm if it satisfies these four conditions. What are they? First off, it's always non-negative for all x. So it's either 0 or positive. First off, secondly, if you multiply its input by some scalar, the scalar can come out, but with some with an absolute value. Why do we need this absolute value? What is the reason? Because of the first condition. The output of the norm must be non-negative. What if A is negative? Right? Also, norm of x is 0 if and only if x is 0. So if x is 0, norm of x is 0. If norm of x is 0, x is 0. Two-sided. And triangle inequality. For this, I always say an example, and I think you understand it by example very well. So consider A, B, C. I have a donkey here. I have food here. I have one path going from A to B and then to C. The other path from A to C. Which path does the donkey choose? A to C. Because the donkey understands that A to C is shorter than A to B plus B to C. That's called triangle inequality. That's why in Middle East they call it qaziyatul himar, or principle of donkey. Okay, principle of donkey. The donkey understands that A to C is shorter. We have important norms for vectors and matrices. So for norms, the most important norm is LP norm. Consider the vector d-dimensional vector x. Its LP norm is defined as this. So you have absolute values of the elements to the power of p. You sum them up, then you add the whole thing to the power of 1 over p. P is greater than or equal to 1. The most two well-known LP norms are L1 norm and L2 norm. L2 norm is also called Euclidean norm, with P equals to 1 and 2 respectively. So if we set P to 1, what happens? We'll have L1 norm. So it's just the summation of absolute value of elements. If you set P equals to 2, you will have L2 norm. So it's the summation of squared elements, the whole thing square root. Right? As you see, for D equals 1, for one of the elements, it becomes the absolute value function, right? As you see here, it is not smooth. So L1 norm is not smooth. However, L2 norm is quadratic. It is smooth. It is like this. We have other norms for vectors too, out of the scope of this course. You can take a look at them, such as nuclear norm, etc. Doesn't matter. For matrices, the most important norm for us is Frobenius norm. Consider a matrix X, but D1 rows and D2 columns. We have Frobenius norm, which is defined as this. You have each of the elements to the power of 2, sum them up, the whole thing, the square root. Its format is very similar to the L2 norm for the vectors. However, you should note that we also have L2 norm for matrices, which is not this. We don't call it L2 norm of matrix. But that's out of the scope of the course because that's mostly in pure math, L2 norm of matrix.
Why do we need norms?
Why do we need norms? Because almost in all cost functions, loss functions of neural networks, we are using norms.
The distance function?
Yes, but by the way, I think I forgot to say the norm here, the definition of norm has 4 characteristics, right? 4 properties. Have you seen these 4 properties for the definition of distance metric too? Distance metric. If you Google it in Wikipedia, it will give you these 3 or 4 properties for this defining distance metric too. When I say distance metric, means distance. The thing that we usually call distance in mathematics, they call it metric. Okay, doesn't matter. So distance metric. Why? Because norm and distance are the same thing. Can you tell me why? Norm of x is just the length of vector connecting origin to that point in different ways. So if you use L2 norm in one way, you calculate this length, L1 norm, L2 norm, different ways. We can calculate this length, right? This is norm. Why? The proof is simple, because this is equal to this. Norm of x minus 0. 0 is the origin, right? So the norm is nothing but norm and distance are the same thing. 2 names for one thing, I believe. Okay. And why are they useful for this course? We almost always have norm in loss function. For example, mean squared error. You can see it as a squared L2 norm. Quadratic forms. You see that a lot in machine learning and deep learning. Squared L2 norm can be seen as x transpose x. Okay. A squared Frobenius norm, you can see that trace of x transpose x, because Frobenius norm of x is this square root of trace of x transpose x. Okay, when you have to the power of 2, the square root goes away. These are both quadratic forms. When I say quadratic form, it means that it's like a bowl. So for 1D, 1dx becomes like this. For 2dx, so the third dimension is the function value, I mean. It's like this, exactly, like a bowl. In 3dx's, where the 4th dimension is the function value, I can't visualize it, you need to imagine it. It becomes a hyperbole, bowl in higher dimensions, right? And the bowl can face anywhere, upwards, downwards, right? Here, if it is like this, a squared L2 norm is facing upwards because it is convex. Minus a squared L2 norm is facing downwards and it is concave. Okay. And don't see these formulas without notation, without attention. That's actually very important. You can put anything rather than x. You can put ben. This becomes ben transpose ben. Rather than ben, I can put what? For example, x minus y. Then what happens? X minus y transpose x minus y. Then this thing becomes x transpose minus y transpose. Then I can multiply the elements to each other. I will have 4 terms. Right? See that a lot in machine learning. Okay. Preliminaries and derivative. That's also important. So, what is the definition of derivative? What is the definition of derivative? In high school or first year of undergrad.
Change of phi with respect to it.
Change of
With respect to
change of y, something with respect to x, another thing, right? Exact. So in other words, when I say derivative of y with respect to x, it means that let me change x and see how much y changes. How much tweaking x impacts y. This is definitional derivative. First people who were thinking about these things were Newton, Leibniz, and these people. Right? Who were founders of differential geometry. Okay, so that's a very simple idea. Now, from this simple idea, you will understand the dimensionality of derivative. Let's see. Okay, in high school, it was easy. Derivative of a scalar with respect to another scalar. It was like that, right? Y was a scalar, x was a scalar. Derivative of y with respect to x is something. So let's change x. Let's see how much it changes y. It gives me some derivative. Why was the derivative of a scalar with respect to another scalar was a scalar? Why was it a scalar in high school? How many changes do I have? If I change x, it changes y. I have only one change, and that change, I call it derivative. Now you tell me, derivative of a scalar, let's make it more complex. Derivative of a scalar with respect to a vector, a d-dimensional vector. What does it mean? I have a d-dimensional vector. Let me change or tweak every element of this vector and see how much does it impact that y, that scalar. Right? How many changes do I have? Derivative of a scalar with respect to a d-dimensional vector. How many changes do I have?
Less than equal to d.
Why less than or equal to d? Why do you this? I have exactly d. So let me, what did I say? Let me change every element of this vector. When I am changing this, the first element, I have the other elements will remain fixed. Let me change it and see how much does it tweak the scalar. Now I go to the second element, the third element until the dth element. How many changes do I have?
D.
Exactly d, right? D changes I have. Therefore, my derivative becomes a vector, a d-dimensional vector. Now, consider derivative of a scalar with respect to a matrix with d1 rows and d2 columns. What is the derivative? So let me tweak every element of this matrix, and it impacts the scalar. How many changes do I have? d1 times d2.
Column of the matrix.
d1 times d2. So the derivatives, you can see it either as a d1 times d2 dimensional vector or a matrix of size d1 and d2, d1 rows, d2 columns. Therefore, derivative of a scalar with respect to matrix is a matrix. Now, derivative of a d-dimensional vector with respect to a matrix with d1 rows and d2 columns. What is it? Let me change every element of this matrix. See how much it changes the elements of this vector, right? I think a simpler example is this. Let me go back to another example which is simpler. Derivative of a d-dimensional vector with respect to a p-dimensional vector. So a vector with respect to another vector, but that vector is d-dimensional, the other vector is p-dimensional. How many changes do I have? Let me tweak every element of this p-dimensional vector. When I change every element of this p-dimensional vector, it tweaks or impacts all of the elements of the other vector. How many changes do I have?
P times d.
P times d or d times p. Therefore, derivative of a scalar with respect to derivative of a vector with respect to another vector becomes a matrix. Right? Now, derivative of a vector with respect to a matrix becomes rank 3 tensor. Rows, columns, and heights. Derivative of a matrix with respect to another matrix is a rank 4 tensor. Right? Did you understand the dimensionality of derivative?
Why do we call it tensor?
You can see because we have different definitions in different subfields of mathematics for tensor. Here by tensor, I mean generalization of matrix to higher dimensions. I agree. We might have the other definitions of tensor in other subfields of math. The name TensorFlow
Yeah.
comes from this tensor, right?
So
Okay.
like a data structure,
What?
data structure.
I don't know whether we can call it data structure or not, but I can say it's a generalization of matrix. If you call matrix a data structure, then yes, sure. So now gradient and Hessian and Jacobian. What are these? Okay, usually, whenever our derivative is a vector, we call it gradient. That's nothing complex. So simply, it happens a lot. When the cost function is a scalar, the variable, optimization variable, is a vector. Derivative of a scalar with respect to a vector becomes vector. And we call that vector derivative, we usually call it gradient. But I myself have written papers where the gradient is a matrix. Doesn't matter. Vector matrix, right? So when it is multidimensional, we usually call it gradient. And we can denote it in various ways. Derivative of f with respect to x. It's a d-dimensional, for example, here. Gradient. Where f gets rd and outputs r. Now Hessian is the second derivative. Okay. You can see it as a second derivative of the scalar with respect to a vector. So when my optimization variable is a vector x, I have a scalar function f of x, but let me take derivative twice. For the first derivative, it becomes a vector, right? Which is a gradient. The second derivative, I should take derivative of gradient with respect to x. Gradient is a vector. X is vector. The derivative becomes matrix. That's why Hessian is a matrix. And we denote it by second derivative of f of x with respect to x2. And also here. So it's a d by d dimensional matrix. Why is it d by d? Because gradient was d dimensional. X was d dimensional. We call it Hessian. I think I have removed Jacobian. But Jacobian, when we have, doesn't matter. Sometimes when gradient becomes a matrix, we also call it Jacobian. Okay. When gradient becomes a matrix, I mean I have f of x. I have several. So f of x, I think, yeah, I can say it in this way. So f of x is rd to some rp. Right? Therefore, I can have derivative of elements of f with respect to elements of x. Right? Therefore, the derivative becomes a matrix. We usually call that matrix Jacobian. Doesn't matter. You can see Jacobian, gradient, and derivative as the same thing. Yeah, the different names for one. The first derivative.
Hessian is also matrix.
Hessian is a matrix, yes. But Hessian is second derivative. Jacobian is the first derivative. Chain rule, I think I don't need to explain it. You already know. Do you know that? Okay, derivative of Benjamin with respect to Jack. You can see it as derivative of Benjamin with respect to John times derivative of John with respect to Jack. Rather than saying that, let me tweak Jack and see how much Benjamin changes. Let's tweak Jack, see how much John changes. Then let's tweak John. Then by this change of John, how much does Benjamin change? Right? This is chain rule. Example of this, consider so derivative of f of x with respect to x. I can say that derivative of f of x with respect to g of x times derivative of g of x with respect to x. In this example, we have g of x is this, and the f of x is square root of g of x. So this is derivative of f of x with respect to g of x, which is a derivative of a square root. And this is derivative of g of x, which is this with respect to x. Right? This is chain rule. We can have multiple chains in the chain rule. optimization. I think I already talked about it briefly, but let me go very fast over it. So consider this optimization problem. Minimize f of x cost with respect to x subject to M1 inequality constraints and M2 equality constraints. Why have I mentioned inequality constraints, all of them as less than or equal to? Because if I have greater than or equal to, I can simply convert it to less than or equal to, right? Don't you agree? Y1x is less than, sorry, greater than or equal to 5. I can say minus 1, y1 is less than minus 5. I rename minus y1 as y hat 1, whatever. It became y hat 1 of x less than or equal to minus 5. I simply can convert greater than or equal to less than or equal to. Why have I put zeros here, not other scalar? What?
Minus.
We want to minimize. No, we want to minimize, but what if we have less than or equal to 5? Why have I put 0?
The constant to the left.
Exactly. Whatever we have in the right hand side, I can bring it to the left hand side, and I rename the left hand side to become y of x. So the right hand side will be 0. Right? So this is the general case, actually. Right? The Lagrangian that she mentioned, the initial minutes of the course, what was it? It's this. So I'm saying that let me embed the constraints into as a regularization terms, add them to the cost. Exactly what we talked about. So I have this f of x, then I have this yix, but m1 of them. So I'm summing them. Also, I have hi of x, m2 of them. I'm summing them up with some regularization parameters, which weights how much yi is important compared to f of x. Right? They have weights. If this lambda I is 0.1, it means f of x is more important. Right? If it is 1.1, f of x is less important. Because the weight of f of x is 1. I can write it in vector form. And then it becomes unconstrained. Now let's take derivative of Lagrangian with respect to x and set it to 0. This is an overview of optimization. But I think we'll not use that. We only use gradient method in this course. So minimize f of x, unconstrained optimization. As I said, we should do it numerically if we can't find it closed form. So this is exactly what all of the numerical methods are. The next x is the previous x plus some step. The whole difference between the algorithms is finding this step. Right? Let's find the step. If we use this step, minus eta. Eta is some parameter, some scalar. Minus eta, the gradient is called gradient descent. If I use minus eta, second Hessian inverse times gradient, so I'm using both first order derivative and second order derivative, becomes Newton's method. What is gradient method? You have used that a lot in your real world life. You go to a mountain, you go to the top of the mountain, you want to come up. Assume there is no road, specific road. You should choose the road. What is the wisest way to choose the road? Assume you are an athlete and you don't fall, okay? Of course, you will choose the road part which for the fastest way. I mean, with this, you will find the path with the highest slope at every step. We want to be at the bottom of the mountain in the fastest way that you can. This is gradient descent. Gradient ascent is the other way around. You want to go up. Okay. And constraint optimization, as I said, is the interior point method that I briefly mentioned. Another method is proximal method. For more information on these, you can see my optimization course on YouTube. Okay, we'll continue the other things in the next session. So eigenvalue problem, singular value decomposition, generalized eigenvalue problem, and then we will move to one neuron and these things. Sometime so I think I will post. I will ask you in the announcement of the course link. I will ask you to watch a 3-hour session. And you have time to watch it until several sessions later. That's about overfitting. I will cover, of course, overfitting of deep learning, regularization techniques of deep learning, and for that I will very briefly review that lecture, assuming that you have watched that session in detail. And you feel free to ask me any questions for that. I will let you know which video to watch. Okay.